First of all, I would like to welcome our keynote speakers, Dr. Paolo Negro and Dr. Akio Kasuga. Good morning, everybody. Ladies and gentlemen, we start our keynote session. Dr. Paolo Negro will give the first presentation. He is research officer at the European Commission Joint Research Center and project leader at the European Laboratory for Structural Assessment. He has a long experience and record of research activity in earthquake engineering and environmental design of buildings. Dr. Negro has been leading many research projects at ELSA, serving as liaison member in the technical committee of ISO TC 71, concrete, reinforced concrete, and recessed concrete, chairing two subcommittees in charge of the drafting new norms and in the technical committee TC 13, seismic design of the European Convention for Structural Steelwork. So I would like to give you the chance to give your keynote presentation, please.
Thanks so much. Good morning in Europe, good afternoon in Shanghai, and I hope also good night in Chicago. I would like to start thanking the FIB organization in China for giving me this opportunity, and particularly to Professor Zhao Bin. I will also mention that I noticed Professor Hayek is on board this morning, and Professor Hayek is a key person as for the subject that we'll be covering. Today, my intention is to report about the work being done in Europe, particularly at the Joint Research Center of European Commission, on integrating sustainability in structural design. In particular, I will focus on integrated techniques for rehabilitating existing buildings, both in terms of energy and environmental issues and structural aspects. The first topic we'll cover is what we call the project SAFESUST, impact of sustainability and energy efficiency on building design or retrofit. This is what we call an institutional work package at the Joint Research Center of European Commission as a part of a general action, safe and clean construction, which covers our support to the development of codes in Europe, in particular Euro codes. The idea of SAFESUST is to define a holistic approach to include both safety and sustainability in design. So we claim we created what we call a SAFESUST approach. Also, we developed what we call a Sustainable Structural Design Method, SSD, to combine sustainability and seismic safety in the design or rehabilitation of buildings. Everything moves from the availability of the life cycle analysis techniques. I will not spend many words about the importance of the life cycle analysis because I noticed that Professor Toenti will cover in detail the impact of our industry on the environment. Dealing with life cycle analysis means using a set of tools which are readily available to label the result of our design, our building, in terms of environmental performance. The key issue as for LCA procedures is that they are all based on different criteria. There is a general lack of interoperability between the different criteria. Applying those procedures somehow long, it requires a lot of expertise, and I might claim it is difficult. And more importantly, the application of LCA procedures done a posteriori, at the end of the design process. You design your building, and finally you run your life cycle analysis, and you get your typically label in terms of performance. If you have done a good design, you might be a gold designer or even a platinum design. Differently, we stick with silver label. This is not suitable for design. Why? Because this stress on environmental performance might hide some typical aspects of structural design, and seismic safety is one. There are many examples around the world of rehabilitation of buildings in terms of energy or environmental performances, for instance, by placing solar panels on the roof, resulting into a disaster and the waste of resources as an effect of a seismic action. So, what would be the correct procedure for integrating environmental issues and structural safety? Well, typically a designer ends up with a design of a building structure, including architectural aspects, and then he or she might check the environmental performance, which might not be fully satisfactory. Then in principle, one should go back and look for a different design solution for having a better performance in terms of environmental issues, but it might not correspond to the smartest solutions in terms of structural behavior. So what we do? Our aim is to integrate the two procedures to optimize all performances at the same time. We move from the idea that owners perfectly understand the importance of energy performance. Why? Very simply because a better energy performance corresponds to lower operating costs. So cost, that's the main issue in our approach, is the parameter which is mostly understood by all people involved in the project. This will guide us in describing how this sustainable structural design methodology works. The first step is the evaluation of the energy consumption expected all throughout the operation of a building. The idea is to define a cost also associated to the structural performance. Sounds crazy, but it is indeed well connected to performance-based design approach, a procedure which I'm sure is familiar to all of you. The first idea of using a performance-based approach was launched in California by the so-called peer method. It is a fully probabilistic approach. It clearly defines all the ingredients of a method. However, I'm sure you join me in saying that it is by far too complicated to be used in day-by-day design. So our idea was to propose a simplified performance-based approach. How does it work? It is divided in 4 phases. One first defines the limit states, which are the typical ones of earthquake engineering: low damage, severe damage, and so on. And at each limit state, a corresponding cost for repair is connected. The limit states are typically defined in terms of interstory drifts. Then we connect these interstory drift values to the corresponding PGA, the peak ground acceleration, corresponding to the drifts in the definition of a seismicity provided by the code. Then we associate to these PGA values a probability of exceedance, which is also provided by the seismicity in the national code. And by selecting an expected lifetime of a building, we can compute the corresponding probability of exceedance by means of this equation. Then it is a game of calculating the corresponding losses at each limit state and multiplying those probability of exceedance times the corresponding cost. The sum of all these costs corresponding to the expected total cost during the lifetime of a building. The procedure is pretty simple, can be worked with a simple spreadsheet, and allows for the definition of the total expected cost to be compared with the cost of construction or rehabilitation. Doing so, we can associate to our design solution a total cost in terms of expected total energy for operating the building, cost of economic losses, which might include all the repair and substitution after seismic events, to be compared with the cost of construction. What is missing? Sustainability in principle should be already taken into account, since energy performance is somehow related to environmental behavior of a building. Lower consumption of energy corresponds to a lower production of carbon dioxide to be put in the atmosphere. But that's not all. We all know that sustainability also relates to a wider definition like a psychoanalysis, and there are some terms which might be disregarded so far, like the embodied energy, the energy associated to the material, to the construction itself, the consumption of raw material, and all the LCA components associated not only to the operation, but also to construction, repair, and finally demolition of a building. How important is this component? Typically, it is in the range of 5 to 10% of the total of the environmental impact corresponding to the operating of a building. However, we all know that the aim is a future of nearly zero energy buildings. In such a situation, this component related to embodied energy might become dominant. So it should be taken somehow into account. Let's go back to life cycle analysis then. We all know how it works. It's a matter of defining stages and boundaries and applying a procedure to obtain a result out of our calculation, which for most, unfortunately not all, the components is expressed in terms of equivalent carbon dioxide emissions across the working cycle of a building. So running an LCA analysis would result into a number which is the total equivalent CO2 corresponding to the construction, operation, and final demolition of our building. So how can we obtain a global performance indicator then? Well, we said that the result of a life cycle analysis is an amount of total carbon dioxide, and the operation and construction of a building can be expressed in economic terms. Comparing carbon dioxides and monetary correspond to comparing apples and oranges. So we should look for a way to combine the two components. The idea is very simple, and I'm proud to say that it corresponds to a very strong statement by the President of the European Commission. Carbon must have its price. We should be able to associate to the carbon dioxide emissions an economic value. And indeed we are. There are already existing markets of carbon. This is the variation of the European Union emission trading systems. There are many others. As you can see, it has very different values on time. It moves from as low as 8 euro per ton, and it is nowadays about 30 euro per tons, we might imagine a situation in which a realistic value should be attributed to the carbon emissions to accurately measure the environmental impact of emissions. Waiting for that, we can explain how to take that into account. I will show you how to do it by reference to a pilot application to a building. The building is a 3-story structure, which was, as for the structure, tested in our European Laboratory for Structural Assessment. And this mock-up was ideally transformed into a real building, an office building in this case, to be located in a particular site characterized by its seismic action. And we worked 2 different design solutions, one of which was the precast solution, which indeed corresponded to the mock-up we tested in our laboratory, and a sort of cast in situ equivalent, defining all the occupancy requirement and defining also the architectural and functional solutions for curtains, flooring, floor systems, and so on. The first step was to complete by means of a Sysma Pro software, the impact of the 2 solutions in terms of equivalent CO2 emissions, and you see the final values in this table. It is also interesting to look at these values by comparing the importance in terms of CO2 emissions as for the different components, internal walls, external walls, and structure. And also to notice that at the end of the day, the value is strongly influenced by the lifetime we have in mind for our building. The expected lifetime was 50 years for this case, but you can notice that having a shorter or longer lifetime might impact dramatically to the environmental performance, which does not come as a surprise. The other step was to evaluate the energy performance corresponding to the solutions, and these are calculations in terms of total electricity and gas consumptions all throughout the 50 years of expected operation of a building. And finally, it was necessary to apply this simplified performance-based design to work with structural assessment. Let's see in details how it works. The initial cost is simply the cost of construction in this case, which was done in our case being kind of theoretical by using European material inventory. The damage was defined with reference to the Eurocode, having in mind the behavior of partitions mainly for the lower damage states. So we set a interstory drift limit corresponding to the damage of structural components, which might have to be repaired or replaced after the expected seismic event, as well as the more traditional damage limits corresponding to heavy damage, severe damage, and life safety. By using the monotonic curve, we were able to associate each interstory drift corresponding to the limit state to the corresponding peak ground accelerations for the two structural solutions being analyzed, and then jump into the definition of a seismicity provided by the code, in this case the Eurocode and the Italian code for the seismicity. The Italian code provides a formula which allows to obtain the return period for each peak ground acceleration value. Once one has obtained the return period, this formula is used to obtain the probability of exceedance corresponding to that return period. Again, it is a set of calculations which can be done by means of a simple spreadsheet. The results are here expressed. You have for each limit state, you have for each limit state the corresponding peak ground acceleration, the return period, sorry, and the probability of exceedance corresponding to that return period. The damage cost has to be defined by the engineer, eventually under consultation with the owner or the investor, because it might also include some sort of downtime considerations. And by multiplying the expected probability of exceedance times the damage, one obtains the loss corresponding to that limit state. By summing up all these expected losses, one may obtain the total expected loss throughout the lifetime of a building. And this was done for the precast structure as well as for the cast in situ structure. Moving to toward the global assessment parameter, we try to combine all the environmental impacts, intending the carbon emissions that we have been defined before by computing the expected consumption and multiply by the unitary terms, the energy consumption, the gas consumption, and summing up the energy consumption and the carbon emission, we obtain the values of the equivalent cost of the total environmental aspects. Then it is just a matter of summing the different components and obtaining the total expected cost for the two structural solutions, precast and cast in situ. And it is interesting to compare for the chosen value of the 50 years expected lifetime, the contribution of initial cost of environmental impact and total seismic expected loss. Here you see the values. And by summing up this value for the two solutions, we can easily define who the winner is. I mean, what is the structural solution which is most efficient in monetary terms for both environmental and structural behavior. We believe that the beauty of this approach is that it frees, for instance, structural engineers from having to deal about different difficult calculations as the application of life cycle analysis tools. Why? Because being expressed as an ultimate value in terms of monetary values, it is perfectly conceived for allowing for the interaction of different aspects. The structural engineer might be able to do his job and provide the corresponding expected the construction cost as well as the expected damage losses during the lifetime of a building. Whereas other specialists, as MEP engineer, might concentrate on the functioning of a building and provide the performance of the buildings in terms of expected operating cost for heating and cooling. An LCA expert might be able to run a simulation tool to provide the equivalent total carbon dioxide emission and then the corresponding environmental cost. A simple sum of these values may be in front of a stakeholder or the owner might drive the consortium of specialists in devising what the best solution is. This approach is also powerful because it might be applied at different scales, and indeed we try to do that. A typical problem in addressing situations like the existing building stock in Europe has immediately to face the issue of limited resources in front of a very old existing building stock. So some planning choices have to be devised. This tool, by sticking to category of buildings, might be applied to define where it is more important to intervene at first. Again, by using a monetary parameter associated to class of buildings, which can be easily understood by all operators, including stakeholders and local authorities. Another strength is that it is not having been conceived for earthquake engineering, mostly for very clear reasons. The performance-based design was conceived in this cultural environment. It has no restrictions as for application to different structural issues. We might associate the behavior of buildings, structural safety in general. And nowadays, there are many examples of situations in which existing buildings should be upgraded as for higher loads requirements, or we might consider transformation and reuse of classes of buildings which were designed for one function and should be transformed for different functions. There is an increasing sensitivity to issues related to maintenance of structures, and this is the perfect framework to conceive the structure which is most efficient also in terms of lower expected maintenance costs. Fire resistance could also be included, and all the effects of climate change will have one day to be included in our considerations. To that extent, I might mention a recent workshop in which this idea was applied to the safety of buildings with respect to actions different from earthquakes, and specifically the risk of global collapse due to local failures induced by explosions. And you might wish to refer to the proceedings of this workshop. Then I will move to a more recent activity, which is currently being performed by the Joint Research Center by direct mandate of European Parliament. It is an activity which is conducted with the assistance of a number of European experts. This project has a scope, and the scope was attached to this project directly by the European Parliament. The scope is to define solutions that at the same time, and also in the less invasive wave, are expected to reduce seismic vulnerability and increase at the same time energy efficiency, so to obtain a lower environmental impact. The main objective is to define tools and guidelines, and that's our technical effort, as well as to stimulate the use of integrated energy and seismic safety solutions to create awareness all throughout the European scientific community, and at the end, by means of providing input to an action plan, increase resilience of the existing built environment. It has a well-defined policy setup. It is immediately associated to the effort for the Green Deal and Renovation Wave, currently active in Europe. It relates to the Directive for Energy Performance in Buildings. It has a strong industrial performance defined by the new industrial strategy for Europe and the new European Circular Economy Action Plan. In our intention, it will fully comply with the action plan for the Sendai framework, particular as for the goal 11, sustainable development. And finally, being designed for the European territory, we keep one eye on existing structures which might have a value as for European culture. Many old buildings in Europe are part of European cultural heritage. It is subdivided in 5 actions. The first 3 are the one related to this topic, to this presentation. The action 1 is a study and classification of the technologies for seismic strengthening. The equivalent is action 2, in which technology for environmental and energy performance are lost. The first one is the independent analysis of existing technology for either structural strengthening or environment or energy improvement, whereas the second is an analysis of the existing technologies for combined amelioration of buildings with an eye on novel technologies. The third action relates to a definition, a practical definition of methodologies for combined redesign of buildings. The other actions are related to regional impact assessment and to the engagement of stakeholders at European level. This is the timeline of our project. It started almost 1 year ago. I'm proud to mention that last week we had our midterm workshop, which was a successful event in which a large group of stakeholders and European experts were involved. We will have more time to go to prepare of a publication, define technical guidelines, as well as to provide our contribution to the definition of European action plan for dealing with existing buildings. A quick overview of the actions. Action 1, we said, is the analysis of technologies for seismic strengthening and energy upgrading in an independent function, out of which we are struggling to define the typical building typologies needing upgrading. At the same time, we are studying all the existing technology options for seismic upgrading, keeping in mind that we want to classify them in terms of economy, life cycle performance, and mainly compatibility with energy upgrading. The other way around is studying technology options for energy upgrading, again with attention for life cycle performance and with particular attention for combining these technologies with seismic strengthening. As for building typologies, a huge work of analysis of the existing building stock ended up with figures which are a bit worrying. A large portion of the buildings is very old and badly need upgrading. We also identified the most typical structural configuration materials, and those are masonry buildings for many countries, but also reinforced concrete old buildings for a bunch of European countries. We compared the climatic zones, and we ended up focusing on the most representative cross situation of seismic safety demands and energy demands, which ended up focusing on Italian territory as the most representative situation. I will not spend much time on our classification of technology options for seismic upgrading. We are all familiar with them, but we are proud to have completed a comprehensive analysis in which all the economic components, cost of intervention, time of disruption, and compatibility with energy upgrading was attached to each one. The same was done for energy upgrading options. A complete review of existing independent options for improving the energy efficiency of buildings was carried out, and all these were classified and ranked somehow in terms of impact, but also, again, cost of intervention, disruption time, and in this case, compatibility with seismic upgrading. An action was devoted to study existing methods for combined upgrading and also novel technologies and materials for energy upgrading. As for the combined existing methods, you see a bunch here. I cannot go in describing them. A typical example is the joint improvement of existing reinforced concrete buildings by placing materials on the claddings to improve at the same time the energy performance and the seismic resistance. But obviously there are many other options more or less integrated. Novel technologies were also studied with covering both local and global measures. And at the same time, we also studied potentially promising new materials and technologies, such as vacuum insulation panels, phase change materials, or glass field panels. But probably the most important action is the definition of the methodologies for assessing to make the method I presented before available to a wider community of technicians. These have three actions: a state-of-the-art assessment of methodologies for combined upgrading, and then a proposal for a simplified method. A third sub-action was the identification of case studies and the application of the existing as well as a simplified method to practical upgrading. As for the state-of-the-art of the assessment method, the work done was a classification of all the existing methods to cover the component of seismic vulnerability, environmental assessment, sustainability, and combined. We stressed the importance on considering anyhow the cost of interventions, and the conclusion was that indeed only the SSD method I presented before is currently available to achieve this goal. The proposal of a simplified assessment method is underway, so I will not be able to spend much to tell you more details about this. It is based on the idea of conceiving a simulation box, which has to be populated by preliminary studies and finally to be used by the designer in assessing in a simple way the result of his or her design. It will have again 3 components, one related to seismic performance, one to energy performance, and one to environmental performance, by defining the corresponding expected structural losses, the estimated annual cost of energy, and the expected environmental impact, again to be combined and be given as a final result of a design process for deciding about the efficiency of a design process. At the same time, we're running key studies with European significance. We identified a number of structural situations for existing buildings, which we claim have the capacity of covering somehow the problems which might be faced in all the European territories. The study is in progress, so far we didn't yet apply the novel simplified technology, but it is interesting to notice that the application of existing methods, the SSD methodology, corresponding to significant reductions in terms of total operating and environmental costs for a typical building. This ends my presentation, and I will be glad to answer any question, if any.
Thank you very much for the very interesting presentation on sustainability and seismic design, seismic performance. We have a little time for questions. I start with my question and I open the floor. Then a short question. You presented step 1, 2, 3 for design phases. My question is there any situation when you have to go back from level 3 for structural performance assessment, or level 2 to 1 or 2, level the previous levels? Yes, please.
It might be. The idea is to avoid the independent design. We are all used to architectural design, which are fully handled by design architects. Then they are transmitted to the structural engineer, who cannot make any change to architectural layout, maybe solving crazy difficulties which were not foreseen by the architect. This concept should be extended.
Yes.
Different actors should play the same role in design, as well as we spend our lives trying to have architects who consider the problems of structural designers.
Yes.
We claim that this should be extended. So people caring with architectural issues, people caring with environmental issues, people having to design the energy functioning of a building, could work independently, but meet together, exchange ideas, provide preliminary results in a common table in which the results are expressed in operating costs, construction costs, environmental costs, which can be easily summed up to reach a common consensus about the way to go. So yes, there is an interaction, but it's done in a simple way, and on top, in a way which can be easily understood by the owner.
Yes, thank you very much. There is a message, no question, from Professor Petr Hayek. Thank you for the excellent presentation, especially for very good and clear case study using SSD. Thank you again. There is no more question.
Hello, George.
Yes.
Yeah, this is Bean. May I ask a question?
Please.
Okay.
Sure, good to see you, Professor Bean.
Okay, hi, Paolo. Yeah, thank you very much for your great presentation. it's really a big system work to consider every aspect of the building's whole life. My question, yes, the questions I'd like to ask is, do you prepare or consider to prepare any software, perhaps a group of software for the associate to use your method? So the second question is, yes, I noticed you have some case studies. I want to ask also, do you have any real applications of your proposed methodology?
So please.
Yes, thank you, Bin, for your questions. These are only meant to remind that we are at the midterm of our pilot project. So obviously we have intention to make all the necessary material available both to the scientific community and to the European policymakers for the definition of a roadmap. So yes, I hope that at the end of our effort, which will be in a bit more than 1 year, we will be able to provide designers with practical tools for implementing this methodology. And at the same time, we are preparing a set of design results for the case studies we have analyzed to be published and also make available to a wider public. So please stay in touch and follow our activity. We expect in 1 year from now to have a final workshop, which will be the final presentation of the results of our work, and not to be forgotten by all our European experts. And once again, I thank Professor Hayek. So stay in touch.
Yes, a quick answer, please. And there is a question from Renata Cotinia. Is the same life cycle assessment procedure for concrete and brick structures?
Yes, why not? I must claim that I'm not an expert on life cycle assessment. Life assessment, like most of you, I expect, is a black box procedure, which is well defined and is as valuable as long as it is based on certified unitary values. So I might claim that there are experts who certify that the database which is built in LCA softwares are appropriate for all materials.
Yes, thank you. And the last question, there is a very important question from Tomo Ueda from Japan. Dr. Paolo Negro, thank you for the interesting lecture. In your lifetime analysis, how do you consider the durability, this means degradation due to environmental actions? Do you assume no degradation for seismic performance assessment usually? This is the question. And we have to finish this part with your answer. Thank you.
It's great to hear from you, Ueda-san. As I said in one of my slides, the procedure was created for earthquake design mainly for historical reasons, because earthquake design was the community in which performance-based design was conceived. I agree that there is much more than earthquake behavior in structural performance. So other components could be taken into account, and durability is one of the most important. Again, it is possible to associate to durability a cost, a maintenance cost, for instance. So optimizing a structure in terms of environmental performance as well as energy performance and maintenance cost could be the perfect play game for taking correctly durability into account.
Yes, thank you very much. Thank you for an excellent presentation. See you again another time. Thank you.
It has been a pleasure. Thank you to all the audience, and thank you for the discussion, which has been very interesting.